All right, so molecular orbital theory is something we need to cover. Electrons can act as particles, they can also act as waves. This is sort of leaning into the wave character. Waves have sort of a crest and a peak, right? Um, a crest and a trough, I guess. Anyway, they go up and down. And if the two waves that you are combining happen to be up at the same time, they're in sync and down at the same time, what you would end up if you added those would be a wave that has a deeper trough and a higher crest than either of the individual starting waves. So that would be an additive situation. A destructive situation would be as one's going up, the other one's going down, and as one's going down, the other one's going up, so that they kind of cancel each other out. And if you added these two waves together, you would have a straight flat line as opposed to a more enhanced wave. If you want to look into this further, there are links to Physics Classroom that talks about it, and then there's an interactive that you can move stuff around and see how here, because that up and that's down, there's a destructive situation, and how this is up and up at the same time. That's a constructive or an additive situation. And you can play with this, and it's kind of cool. Anyway, if we apply that to bonding electrons, then the 1s electron and the 1s electron can combine into a bonding in sync situation, or they can combine into a not in sync anti-bonding situation. So they have those two options. As you might have guessed, the bonding situation would be of lower energy. So if the electrons go in there first, they would prefer it because it's lower energy. And then only when that's full would the electrons want to go into that anti-bonding, what we call sigma star um, orbital. So let's take a look at H2. H2, each hydrogen brings an electron. Those electrons, since there's only one each, would first occupy the bonding orbital that is lower energy, which is the sigma 1s. There would be no need to do a sigma star 1s or the anti-bonding orbital. And so that would be great. And that's why hydrogen stays bonded. Um, and that's that, I think. I think you're good with that. All right. Bond order helps with this. You might want to write this on your card. It's a formula you will need. The bond order equals the bonding electrons, so the stuff that's in the bonding orbitals minus the ones that are in the anti-bonding orbitals divided by 2. So going back to this hydrogen example, you're only looking at the middle stuff here, the bonding orbitals. You're not looking at where they came from. So since hydrogen has 2 electrons in the bonding and no electrons in the anti-bonding, it would be 2 minus 0 divided by 2 is 2 divided by 2, which is 1. And since that's a positive number, that means bonding wants to occur. If you had helium, helium would bring 2 electrons to each of these. So each helium brings 2 electrons to the bonding situation. The first 2 will go to that more stable sigma bonding. The next 2 have to then go into the antibonding. And because they went into the antibonding, and because there was 4 total electrons and they had to go somewhere, 2 minus 2 is 0. 0 divided by 2 is still 0. So that's why helium-2 doesn't exist, according to molecular orbital theory, is because there is no bond order. So if helium was a +1 ion, so if you had He2 plus 1, one of these wouldn't have an electron, right? So you'd only have 3 electrons, and therefore you would have a bond order that was positive because you'd only have 1 electron here. So if it was He2 with a positive charge, 1 electron disappears. That means you have 2 minus 1 or a 0.5 bond order. And then people who get excited about this stuff will try to make that in a lab. And apparently, if you read enough, they've done such things in super high energetic gas phase for half a second, and then they publish it and they get all excited that it helps support this theory. All right. So remember how the p orbitals, there are 3 of them. There's the x orb, there's one on the x axis, there's one on the z axis, there's one on the y axis. They look like dumbbells. So if there are 3 p orbitals, it should make sense that the p's combine to make 3 bonding and 3 anti-bonding. So there's 3 situations where they're all in sync, and there's 3 situations when they're not in sync. Also recall we had pi bonds. So the pi bonds are of lower energy. Then you have the sigma. Then you have the anti-bonding pi, and then you have the sigma pi. These change around, but we're not going to get into it. The point here being, if you have 3 orbitals getting together with another 3 orbitals, you can make 6 orbitals, 3 of which are bonding and 3 of which are anti-bonding. So nitrogen, when it comes together with another nitrogen, if you think about it, it's 1s2, 2s2, 2p3, right? 3 electrons in the p's, 3 electrons in the p's. They all want to go to the lowest energy first. So they're going to occupy all the sigma or the pi 2p and then the sigma 2p bonding orbitals. None would go in anti-bonding orbitals. And so N2 is a nice thing that would do this. And if we're looking at that from a larger perspective, all right, so if we look at the full view of N2 then, where N2 has 1s2, right? 2 nitrogens are bringing 1s2. So 2 of those electrons go into the bonding and 2 of those electrons go into antibonding. The 2s2, 2 nitrogens coming together, the first 2 electrons go in the sigma bonding, the next 2 go in the antibonding, and then the 2p3, each nitrogen's bringing 3p electrons. All 6 will go into bonding molecular orbitals. None will go into antibonding. So if we're doing the bond order, we got 2, 4, 6, 8, 10 are in bonding orbitals. 2, 4 are in antibonding orbitals. 10 minus 4 is 6. 6 divided by 2 is 3. So the bond order of N2 would be 3, or that triple bond that we see. And that's it.